Okay, so we learned about how to solve limits analytically. There are some practice problems that I would want you to do. I'll give you 4. Okay. That one is good. That one is good. And these look similar. You don't notice. Because I want to get used to the similar ones. And then we'll do one trick. And then we'll do a general one. If you get the point. As h equals 0 of that's a good one. So do those problems. I don't have them on the board now. This one's a lot like our tree example. That one's a lot like our radical example, rational example. This one's more like a general, but it's a little bit harder. It's kind of like that one. Do the same way as that one, but with the general kind of variables. Okay. Hopefully you got those problems. Okay, so let's move on from limits. Now before we talk about something super cool, super different and radical, we are going to have to talk about this one concept that is about continuity. Continuity. Important topic, continuity. Okay. Like, what does it mean to be continuous? If we have a function, right? If it's continuous, meaning when you draw it, you know never lift a finger. You never lift a finger when you draw. This function will be continuous. Now, there's a more precise definition of a function that's continuous using limits. So, if a function is continuous, it has to follow these rules. And here are the rules. If a function is continuous at a point, function is continuous at a point. Here are the rules. No. Okay. If a function is continuous at a point, f of a, meaning that point is defined, exists. The limit as x approaches that x value exists. And the limit has to equal f of a. Okay. So let's check a point on this graph. Let's check this big point right here. Is the function continuous on that point? Yes, visually it is. Let's check it. Does f of a exist? Is this point defined? Yeah, this x value right here is defined. There's a definition. And that's right here. Does the limit exist? Well, let's see. Yeah, it sure does. And does the limit equal f of a? Let's try again. Oh, it does equal f of a. Then it's continuous. So that's the definition. Of continuity at a point. That makes right. Now, we can precisely define this limit if the limit as x approaches a from the left equals the limit as x approaches a from the right, and then the limit as x approaches a exists. That is the definition of a function whose limit exists. If you're coming from the left and the right and they both equal the same value, that's what we're doing, then the limit exists. These are the guidelines. You gotta put Let's talk about tangent. Sorry. Before we talk about tangent, let's talk about this function right now. Yeah. What does this look like? Wait. Before we look at the graph, is there any problem with the graph? Sorry, with the thing. Is this function continuous everywhere? Well, let's plug in 2. That's the only problem we have. It doesn't exist. 2. Let's plug in 2. It's undefined. But before we do that, what's the limit as x approaches 2? Well, we can take the limit and equal 4. Okay, does f of 2, not defined. So the function is not continuous at 2, in fact, it's continuous everywhere except 2. And 2, x equals 2 is what we call a discontinuity. A discontinuity at x equals 2. And this looks like one of those holes. Now, there's different types of discontinuities, meaning things that don't make this continuous, things that cause problems, called discontinuities. If you have a hole, it's a removable discontinuity. The reason why it's called removable is because you can simply fill it in like that, or you algebraically remove it. So, there we go. Remove discontinuity at x equals 2. Okay. What about y equals absolute value of x minus 1? Okay. This one's a little bit weird and tricky. If we were not to use a graph, and you would take limits, well, if you plug in any number, it'll exist, right? But there's an iffy-biffy thing with absolute value. And we have to change it into its piecewise form. For normal absolute value, it is x if x is greater than 0, and it's negative x if x is less than 0. That's what absolute value of x is. But x minus 1 if x is greater than 0, and it's negative x minus 1. And so and then okay, so we have to make this absolute value function into a piecewise function definition. Now here's its saying. You have to take one-sided limits when the piecewise function changes definition, meaning it changes definition when x equals 0. So we have to do this. We have to check and make sure these are equal, because otherwise the function is continuous everywhere because polynomial. It's continuous everywhere otherwise. The only problem is when we have a change in definition. Because we know this is a polynomial and this is a polynomial. And we know those are continuous, but when the function changes definition, we could possibly have something that looks like this, and the limit doesn't exist. Therefore, there's a non-removable discontinuity because you can't remove it. It's just stuck there. So we have to do one-side limits, check if they're the same. So let's do this. What is this? Well, you can just plug it in. Honestly, you can. This is what? A negative 1? There you go. What is this? How do you do one-sided limits? Okay. So from the left side, you have your negative. You're making your negative definition from your left side. Left less than 0. From the right side, you're using that. So from the right, meaning you're going to plug in something very small, positive, because you're going to the right. If we plug in something very small, positive, -1, what are you going to get? Basically, you're going to -1. If we plug in something small negative here, because we're going to the left, we're going to something really, really small negative. Something really, really small negative, something really small positive. That's what we're doing. We're going to have a negative. Doesn't matter what it's going to be. It's going to be a negative. What's going to be a negative? It's going to be negative. Okay. What does this graph look like visually? Oh, I'm sorry. The function changes definition at 1. Cut everything that's before the function changes definition at 1. So plug in 1 here, you get 0. Plug in 1 here, you still get 0. They're the same. It's much faster. I'm sorry. This graph looks like this. It's continuous. So because these two limits exist, that means the limit exists, that means it's continuous everywhere. So there's no discontinuity. Now let's talk about our trig function. And then we'll be done. So let's talk about tangent real quick. We have enough time. Okay. Tangent x. Where is tangent have discontinuities? Well, it's a trig function. We know the graph. It's discontinuous at 0, and it has asymptotes. It's not. Okay, so it looks like this. Pi over 2. The next one is 3 pi over 2. This one's negative pi over 2. Negative 3 pi over 2. So, this is the equation of the asymptotes. That's where tangents are defined. It's discontinuous because there's an asymptote and the limits don't exist. Now, how do we write that? It's a removable discontinuity because it's an asymptote. So, it's discontinuous at, and we have to make an equation for all the asymptotes. At what, x equals what? Well, we know one of them is pi over 2, right? How do we get back this? Well, we add a pi, right? We add a pi. If we add pi, which is 2 pi over 2, right? That's 3 pi over 2, right? You subtract pi, and you add pi every time, pi, to get the next asymptote. And we create this equation like that, such that n is an element of all the integers. But the way, this is just an equation of all the asymptotes. If we plug in any integer into n, we'll get another asymptote. It'll be discontinuous. That just says n can be an integer. That's just a notation thing. So tangent has an asymptote starting at pi over 2 and adding or subtracting pi. That's how we do it. And they're non-removable. Okay. And remember, the limit as x approaches pi over 2 from the left, and the limit as x approaches pi over 2 from the right of tangent. From the left side, we're going really, really high up. Vertical asymptote always has this infinity thing. From the right side, it's going literally down. Negative infinity. That's how limits apply to this. So that means the limit overall of tangent as x approaches pi over 2 does not exist because its one-sided limits don't exist. Therefore, we have a non-removable discontinuity at every x equals that. There you go.